Okay, in order to understand chemical equilibria, we have to first make sure we know what we mean by a reversible reaction. And a reversible reaction is one in which the product can react to come back and give us the original reactants. So where A and B here are our reactants, C and D are our products. So the reaction can proceed in the forward direction, forming the products, but then also the products can reform the reactants. Now, there are a few key examples that you're likely to see over and over again. Some will be familiar even from GCSE. The most obvious one is probably the Haber process, where we have nitrogen reacting with hydrogen to produce ammonia in a reversible reaction. We'll also later on in your transition metals topic, you'll come across the contact process, which is where sulfur dioxide reacts with oxygen to produce sulfur trioxide. And it's so important that you really understand chemical equilibria because we see this in a number of other topics in year 13 as well, particularly in your acids and bases topic, which is actually called acid base equilibria. So we're going to need to employ lots of this understanding, not just in this particular topic, but throughout your A-level study. Now, one key feature that we need in order to achieve equilibria or dynamic equilibrium is our system has to be closed, which means that our reactants and our products cannot leave the system. So if we think of these four boxes, and this is representing a reaction progressing over time, at the beginning, we only have our reactants, A and B. Over time, we start to produce our product, C, and then we produce more C. But because our products can't leave and our reaction is reversible, our product C can then react to give us back A and B. So we can see that we have got a change in concentration of our reactants and our products as we have a reversible reaction. Now, eventually, if we have a reversible reaction taking place in a closed system, we are going to reach a state called dynamic equilibrium. Now, the first property of a reversible reaction that has reached equilibrium or dynamic equilibrium is that the forward and reverse reactions proceed at equal rates, aka the rate of the forward reaction is equal to the rate of the reverse reaction. Now, we can show that graphically through a graph where we've got rate on our y-axis and we've got time, or like the progress of the reaction, on the x-axis. Now, at the start, if we just start by monitoring the rate of the forward reaction, which I'll show with a red line, at the start, the rate of the forward reaction is going to be the fastest. And that's because at the start of the reaction, we only have reactant particles. We've got the greatest number of reactant particles, so we're going to have the most frequent successful collisions, so we're going to have the highest rate. So we're going to start up here. But gradually, as the reaction proceeds, the reactant concentration is decreasing. And so if there are fewer reactant particles over time, then we are also going to have a slower rate over time as well. So the general shape of our curve would be a decreasing rate that eventually plateaus. Pretend that's a straight line. Okay, use your imagination. That's our forward reaction. Now, for our reverse reaction, I'll use purple because why not? At the beginning, there are no product particles, right? We've only got A and B here. We've only got our reactants, which means that at the beginning, our rate of reaction for our reverse reaction, which is our products going back to the reactants, that's going to be 0 because there are no products yet. But over time, as the products start to form, the rate of the reverse reaction is going to speed up. And it's going to gradually speed up until it is equal to the rate of the forward reaction. That's a much better straight line. So at this point, where the rates of the forwards and reverse reactions are the same, right? They're at the same rate. This is where we have reached equilibrium, or that's not even a U. We have reached equilibrium, aka dynamic equilibrium, because the rate of the forward reaction is equal to the rate of the reverse reaction. Now, this is not the only way that we can graphically show when a reversible reaction has reached equilibria. So let's look at another type of graph. Now, the second feature of a reaction that has reached equilibrium is that the concentrations of the reactants and products remain constant, or there is no net change in the concentrations of the reactants and products. And that's because the forward and reverse reactions are occurring at the same rate. So as soon as the products are formed at the same rate, the products are reforming the reactants. So we don't end up seeing a change, even though the reaction is still technically proceeding. Now, because we can explain equilibrium in terms of the concentrations, we can also demonstrate this on a concentration time graph, where instead of plotting curves to show the rates, we're plotting curves to show the concentrations of the reactants and the products over time. So there are three well, more than three, but there are three main examples of graphs that we can see for this type. So if I say that my purple line is for reactants, let's just even underline reactants with purple, and then we'll have our blue line as our products. So if we consider what's happening over time, as mentioned before, the concentration of reactants is going to decrease over time, right? As the reactant particles are reacting and being used up. And then we have the same thing, or the opposite rather, for the products. At the start, we've got no products, but gradually the concentration of the products are going to increase over time as the reactants are forming them. And then once we get both lines that are horizontal, that means that the concentrations are no longer changing. And that means that once both lines are horizontal, let's say it's around there, that means that we have reached equilibrium, right? The concentrations remain constant. They're no longer changing. But what is incredibly important to remember, stick with me, is that despite what this particular graph looks like, at equilibrium, the concentrations of the reactants and the products are not necessarily going to be the same as each other, right? In this example that I've just blocked here, okay, in this example, it just so happens that the concentrations of our reactants and the concentration of our products, if we say that the purple, that's our reactants, and then these are our products, we happen to have the same concentrations of both of those at equilibrium. And here we would say that the position of the equilibrium is in the middle. But that, as I mentioned before, and I will emphasize, is not always the case. The concentrations remain constant does not mean the concentrations are going to be the same. So let me show you the examples of when that is the case. So in this second example, we can see we've actually at equilibrium got more products than reactants. Okay, so how would we represent that graphically? Well, it's the same overall principle in that the concentration of the reactants are going to decrease over time as the reactant particles are being used up, and the product concentration is going to increase over time, but it just so happens that when the lines become horizontal and so the concentrations are no longer changing, which is about here where we've reached equilibrium, because the lines are flat and the concentrations of reactants and products remain constant, but we've got at equilibrium more products than reactants. And so in this example, we can say that the equilibrium lies over, do I know my left from right? Lies over to the right-hand side or over to the products at equilibrium. Again, the concentrations remain constant, but there still might be an imbalance of which one there's more of at equilibrium. The last type, if we've got a reaction that at equilibrium lies closer to the reactants, right? So this in this case, we can say the equilibrium lies towards the left or towards the reactants. What would that curve look like? Concentration against time. Again, same general shape. The concentration of reactants is going to decrease over time and then gradually plateau once the concentration no longer changes. And then the concentration of the products is going to gradually increase over time until the concentration no longer changes. Now, once both of these curves have plateaued, once they're flat or they're horizontal, so let's say that's around here, then we can say that this system has reached equilibrium because the concentrations of the reactants and products are now remaining constant. They are no longer changing. It just so happens that at equilibrium for this example, there is a greater concentration of reactants than there are products. And so our equilibrium position is over towards the left. Okay, let's summarize. Let's summarize because we've done quite a lot here. In a reversible reaction at equilibrium, two conditions. Number one, the forward and reverse reactions proceed at equal rates, and the concentrations of reactants and products remain constant. But that doesn't mean that the concentrations are the same as each other. It just means that they are not changing. You need to be able to spot the time at which a reaction has reached equilibrium based on a rate time graph. So that's the one at the left. That's when the rates are equal to each other. And from a concentration time graph, which is where the lines become horizontal because the concentrations remain constant. Now, the position of the equilibrium, left, right, or center, can actually change based on changing conditions, but we'll look at that in another video where we talk about Le Chatelier's principle. So make sure that you have liked this video, leave a comment if you've got any questions, and make sure that you're subscribed so you see the other videos on equilibrium and on all of the other topics across your A-level chemistry.